Dude, I need stress from this week. What do you do tomorrow morning? Yeah, like 10 o'clock-ish? I'll be at 5. Yeah, I can after you next one.
Okay, class. So first thing, questions about anything we've covered, any problems? We keep getting this question repeated. The quizzes are always over the last couple of homeworks, last 2 or 3 homeworks, so they're always cumulative. Go ahead.
332, where specifically second part, where it changes from row to A.
Okay, can you help me with that one second? Just read it. Can you all hear me back there? And if you can't see the picture, wave that. If you can't see it, let me know. I'll either move you or I'll right there. Go ahead. Just tell me what the problem is. Anyway.
Okay, given a 2 centimeter radius solid wire centered on
The axis.
the Z-axis,
Here, let me just draw it up here. We've got a wire that's solid. It's got a radius or diameter.
in a radius of, 2 centimeter radius.
Okay, so this A here is 2 centimeters. Go ahead.
And then with a charge density of rho sub B,
The volume charge density is, go ahead.
6 rho centimeter.
6 rho, go ahead.
Coulombs over centimeter cube.
Centimeter cubed, go ahead. That's inside. So inside the wire, that's what the charge density is. Y'all follow me? Outside the wire is 0. This is inside, so you can say rho V outside would be 0. And this would be for rho greater than A. Can y'all follow me? Go ahead.
Plot the electric flux density
Versus radial distance.
versus radial distance.
All right, we're going to do that. Now, can you all envision the problem? You got a wire, a fat wire, if you will, and it's got a varying charge density. Now, we're going to use Gauss's law to solve this. Remember, Gauss's law is useful and there's a high degree of symmetry. How many see this as a cylindrically symmetric problem? Everybody? Anybody not? If you envision this and you're on the z-axis, no matter how high or how low you go, it looks the same. Do you all agree with that? Now, if you move off a distance rho off the z-axis, this is the z-axis, by the way. If you move off a distance rho and you spin that wire around, it looks the same. There is no variability, so it is cylindrically symmetric. Does that make sense? Now, with that in mind, we have to find a Gaussian surface that will work so we can apply Gauss's law. Gauss's law in the integral form is the integral of b dot ds over the closed surface, whatever surface you choose. And we always find one where there's a high degree of symmetry, so the magnitude, the d field on that surface will be constant. And that's equal to the charge enclosed. Are you all with me, class? So here, it's cylindrically symmetric. The surface we're going to choose is going to be a cylinder. You all follow? There are two regions we have to worry about. If we choose a cylindrical surface and it has a height h, what do I always make h, class?
1.
If given a choice?
1.
1, right? Don't ever make it more complicated than need be. So just let the height of this be 1. It would be true if it was 5 or if it was 0.5. Y'all follow? Make it 1. Now this is a radial distance, rho. And this, the outer surface, is my Gaussian surface. When I look at this, it's the integral of d dot ds. I mentioned this last time. Please hear me. Why am I not going to concern myself with this surface right here or the bottom surface? Class? Say it again.
There's no electric field.
There is no d field that is perpendicular. The d field is radially outward. That is an assumption. Do y'all follow me, class? And that means the dot product of d dot ds would be 0 on top. Something I have to say about dot products, and I'll repeat this several times because I know people will make mistakes with this. Whenever you have a surface, doesn't matter what the coordinates are, there's going to be an area on that surface. So when we take a look at the differential surface vector, there's always going to be a differential area. That's a scalar value. It has no vector sense. But the surface vector will always have a perpendicular component. And that's the normal to the surface. So that's how you get ds for a surface. Do y'all follow me? So if you were in the xy plane and you want a differential surface, the area would be dx dy, and the normal component would be az. Do y'all follow me on that, class? How many understand that? It's the general trend. So if you broke this up, we could break it into two integrals. We could say ds here would be the integral of d rho a rho dot ds, and this would be the outer surface. The outer surface would be rho d phi dz in the a rho direction. This would technically be a double integral, and it would go from phi equals 0 to 2 pi, and z goes from 0 to h. Now that would be the integral of b dot ds on the outer surface, this surface here. Do y'all follow? Constant rho. Can y'all see that in the far back? But there's also going to be the possibility of the integral, and it would be of d on the top surface here, but that's d rho right here, or I should say d rho a rho. I'm just doing this for one time. D rho a rho, but it's then dotted in with a differential surface up here. That differential surface is going to be d rho times, and then it's going to be rho d phi in the az direction. This would be a double integral, and it would really be from, rho would go from 0 to actually rho. You might as well prime these if you want. And then phi goes from 0 to 2 pi. And there would be the corresponding one down here. This would be the top surface, this is the bottom. Now the point is, here I have a rho dot az. Do you all see that, class? What is a rho dot az? Class?
0.
It's 0. Anytime you dot product a vector with an orthogonal component, it is 0. Ax dot ay is 0. A rho dot az is 0. A phi dot a rho is 0. Do y'all follow me on this, class? This is important. So we don't need to do this integral or the bottom one because the dot product is 0 there. We only need to do that one. Now over here, we also have to do one other thing here. There's going to be two parts to this solution. The first part is going to be for rho less than a. That's inside where the charge exists. Do y'all follow me? Here, that's the correct integration on this side. It's really just the surface of the cylinder times d rho. And over here, it's going to be the charge enclosed. Well, technically, this is a triple integral of the charge density. And I hate when he puts it in terms of centimeter cubed. Let me just fix this. See how he has its coulombs per centimeter cubed? I always go to
coulombs per meter cubed. You all follow me, class? I keep it straight MKS. So what is this going to be? It's going to be rho V is equal to what? 6 rho, and then a centimeter cubed is what? 10 to the minus what? Minus 6 meters cubed, right? Y'all follow me, class? There's what? It's 10 to the minus 6. So you can multiply this by 10 to the 6, and then you would get coulombs per meter cubed. Y'all follow? I hate centimeters. I turn everything into meters, kilograms, seconds. I don't mess around with any of the centimeter garbage. Sorry, stop. If I can help it. Because you mess up units. I have. I don't want to. So here, now I'm going to put the charge density, the total amount of charge in this surface is that charge density. So it's 6 rho times 10 to the 6. I'm going to omit the units because they're applied. Then I have, now I have to have a differential unit volume in cylindrical coordinates. The order is not important. You know you're going to have what? You're going to have d rho. That's the radial vector, right? Then you're going to have rho d phi. That's going to be the wiper arm length, right? And then you're going to have dz. Here, rho will go from 0 to rho. So technically, I'm supposed to prime these things. Y'all remember doing that class? Because I'm integrating something, and you can't have a limit of integration with the symbol of anything in the kernel of integration. Do y'all remember that class? It's just, engineers don't really prime things in the real world when they have to do something. But I'm doing it just to make sure you're aware of some of the general trends. Phi goes from where class? From 0 to 2 pi. And where does z go from? 0 to 1. H is always 1, right? Don't make h anything but 1 unless you have to. Y'all follow me on this? It'll save you trouble. All right, now let's just do this, and you can see what happens here. What is a rho dot a rho? Don't guess, right? Think about it. It's 1, right? Anytime you have the same unit vector and you're dotting it into each other, it's 1. A cross product is different. A rho crossed a rho is 0, but don't guess. All right. So here, that goes away, right? Now just do this. And I'm going to tell you, this whole side of the integral right here, it's just the area, it's the surface area of that cylinder. The perimeter of a cylinder is 2 pi rho, right? And the height is 1, so it's 2 pi rho. That's it, times d rho. Now we can do the integration, you can see it. But here, what do I get? When I integrate d phi from 0 to 2 pi, I get 2 pi. I have rho in there, dz from 0 to h, and h is 1, is just 1. So this is simply 2 pi rho d rho on that side is equal to, and what about over here? What happens? I'm going to take the 6 times 10 to the 6 out in front. And what do you get here? I have rho prime squared, don't I? Because I have 2 of them, class. Y'all see this? D rho prime, that's rho cubed, right, over 3, right? So, and it goes from 0 to rho, so this is going to be rho cubed over 3, first integration. D phi goes from 0 to 2 pi. That's just 2 pi. And dz goes from 0 to 1, so you don't need to worry about it. Do y'all follow me? What do you notice right off the bat? 2 pi goes away. Agreed, class? The next thing you notice is you divide by rho here, don't you? On both sides. So we get d rho equal to what? That's just equal to 6 times 10 to the 6th. Then I had rho cubed becomes rho squared over 3, or you can write it as simply 2 times 10 to the 6th. And this would be rho squared. Good for rho greater than 0, less than a, and a is in this case 2 centimeters. So this is going to be inside the cylinder. And does everybody agree with that? All right, now let's go outside the cylinder. Now let's go for rho greater than a. And if you write the equation, the integral of d dot ds over the closed surface is equal to the integral of rho v dv inside that surface, correct, class? This is important, you see this. My second surface is gonna be at a distance rho, where rho is outside, it's greater than the radius A. Remember, there's no charge out here at all when we're at a distance greater than A. So if my surface here, same cylinder in height and shape, only the radius is much greater. Do y'all follow me? Let me see your hands if you see it. I'll move along quickly if you do. All right, I'm just gonna go ahead and plug in this interval. It's really the surface area, right, times the d field. Do y'all agree with this, class? So the surface area is gonna be 2 pi rho times the height of 1 times d rho. On this side, it's the amount of charge, right? Well, if you look here, same integration as I have here with one exception. What is it? Where does rho go from? From 0 to A, right? Because that's where the non-zero charge density is limited to. Do y'all follow me? So on this side, we're going to limit this integral from 0 to A. You agree with that? Y'all follow me? All the charge is contained inside this wire. So when we do the charge density integral, we only have to take that charge density, it's non-zero, out to A. That's it. Do y'all follow me? Take a look at it. What happens? When we do this integration, I could write it again, I'm trying to save time. When you go ahead and do the phi integration, it would just be 2 pi. When you do the z integration, it's just 0 to 1, so forget about it. When I do the rho squared, I got 6 times 10 to the 6, I'll write this down. I have that, but when I get rho, here I have what? Rho squared d rho, it's rho cubed over 3. Do you agree? It's evaluated from 0 to A, so this becomes simply A cubed over 3. Now A is given as 2 centimeters. We'll substitute that in. Does everybody follow me why I did what I did? You asked the question, everything good? All right, now I'm going to just simplify this. The 2 pi's go, right? 6 by 3 is 2. And you can see here, d rho is what? Well, it becomes 2 times 10 to the 6th, and then I have A cubed. A is 2 centimeters, so it's 2 times 10 to the minus 2 cubed. All this is going to be over rho. I'm just doing this for completeness so you can see it. I'm just plugging in values. One thing you see for sure, it's going to vary as 1 over rho. And you can do the math on this one, but this becomes what? It's going to, well, here I got 2, and 2 cubed is 8, right? So that's 16, class. Do you agree with that? So I have 16, right? Over rho. And by the way, 10 squared cubed is 10 to the minus 6 times 10 to the 6 is just 1. Do you agree with that? Did you have a question? You're looking like.
No, I'm good.
Can you read it? Okay.
Yeah.
Can you guys in the back see this? All right, so that would be for rho greater than A. The units are this are going to be coulombs per meter squared, by the way. So if you plot it, how about if I plot it right here? I ask for plots all the time, sketches, because that tells me if you understand what you're actually doing. If you don't know how to plot something, chances are you don't have a clue what's really going on. So if this is D of rho, and this is A, and you're plotting it, over here, this is proportional to rho squared. Do you agree? What's the value of this when rho is 0? There are no wrong answers. 0, right? 0 squared is still 0. So it starts at 0, it goes up, and it asymptotically hits this point. We can evaluate that. And it'll be continuous here, and then it starts coming down to 16 rho at that. It comes down like this, and this would be a value of 16 over A as the peak value, and that would be it. Is that what he have in the book? I don't know. Does he have that in the book? Yes, sir. He does?
He does have that.
All right, how many understand this? It's a fair question. It's a good question because it really identifies how you apply Gauss's law to a symmetric system. Did you guys have a question back there? I mean, if you,
I was just looking at the graph.
I hope it's the same one he has in his book. And it's straightforward. There's nothing tricky about this. Any other questions?
Where's, can you show again, where's the A?
A is the radius.
Where?
A is the radius of this wire. It's limited, right? All through, inside of A, you have real charge given by 6 times 10 to the 6th rho, right? But outside that point, rho V is 0. Does everybody understand that? That's the reason you break it down to 2 integrations. One inside of A, rho less than or equal to A, and the other outside. How many understand this one? You good with that? All right, other questions? All right, let me do a bit of a review. I'm gonna go through some stuff. I'm gonna show you a few other, by the way, for the spherical one, we should do it. I always give you a problem, not this quiz, but I almost always, on any exam, I will give you a quiz that requires you to understand cylindrical and spherical symmetric problems. Did you hear me on this? We'll do it for resistance and like the D field. You're going to see capacitance and other things pop out, but I'm just telling you, you have to understand how to exploit symmetry, or you'll really not make it in this course. And that's probably true when you had physics too. I don't know what they asked you, but I can imagine. And, oh, what am I doing with that? This is good, I should use this. All right, just a brief review quickly, then I'm going to move on. If you have a point charge Q, and I'm a distance R, I call it D away, what is the magnitude of the E field here? Charge Q, distance D, people. It's got to be proportional to charge, right? Whatever Q is, inversely proportional to 4 pi epsilon naught, right? And D squared, whatever D is, right? What would the vector direction be in the generalist sense? It would be A rho, really, right? Or AR. It would be pointing away. I'm just trying to give you a generality. Y'all with me, class? If you had any number of point charges around here and you wanted the electric field at a point, you would add up the electric fields vectorially from all the point charges. Does that make sense? All right, that's a point charge. If I have a line charge, and say this is rho L, like doesn't matter what axis it's on. You all remember that? And I wanted the actual, say the E field, we'll go E field. From that line charge, I had a particular point here. And it's got rho L. The form of this is what? It's proportional to the charge density on the line charge. It's inversely proportional to 2 pi epsilon naught rho. That would be the magnitude. Rho would be a measurement of the distance from the axis of the charge to the point of observation of the field. And remember, it could be on the x-axis, y, or z, or it could be off-axis. Do y'all remember this? We did a problem. Now, the vector direction is A rho, right? But the way you get A rho, if this radial distance here, you could call it rho. Sometimes it's a little confusing. I'm going to call this distance r vector from this point to this point. And you know, r vector, you always get by taking the coordinates of the point of observation minus the coordinates, the associated coordinates of the source or on axis point, and then multiplying by the appropriate unit vector. How many understand that, right? How to get that unit, how to get a vector r. So here, A rho would be equal to r vector over r vector magnitude. The reason I'm doing that is because it's very important for you to be able to do this. Now, That's one charge, right? One line charge. Y'all agree? What happens if I have two line charges? I'm trying to do this so you can understand this easier. Suppose I have two line charges, both infinite, call this rho L. Here's the origin 0. Here's another rho L. Say this separation is D. This is the one we did in class. Same magnitudes, but they're moved off axis. So this is, say, the Z axis. It doesn't matter what axis. Y'all follow me? If I wanted the electric field on this axis, call it the x-axis at a given point. Can you all imagine this? It's a little, I've got two infinitely long charge distributions. Now I'm on the x-axis and I want the electric field at a point on that axis. Do you remember this problem, class? How many do? We did this. This is a good problem. So what you would do is find the actual component of the electric field from that charge distribution. You can call it A1, and you would add to it. Boy, it's going to be tough to show the same way. The electric field from this component right here, and you would find one thing. It's not drawn very well, but you would find that the horizontal components would cancel, but the x components would add. Do you remember doing this, class? How many do? All right. That's important to see. That's applying symmetry to simplify the difficulty of getting the solution. Now, the next thing we talked about is spherically, these are two line charge. Let me do the plane of charge too. These are problems in, I think, the last section, but you can see how it's important to understand how to figure out what the electric field is from these, and you can get the electric field from any symmetric charge distribution using Gauss's law, and then if you have more charge distributions, you simply add the electric field component from each. So if you had a plane of charge, and I'm going to assume this plane of charge is, say, in the xy plane, if you had an infinite plane of charge here, rho s, and this is in the xy plane, and I wanted to know the electric field at a certain height h above it. Y'all follow me? Call this the z-axis. So this is xy. I have a charge density all over this plane of charge. It's infinite in extent. And I want to know the electric field above that. What is it, class? Now we went over that. You're going to have to know these, right? You got to know them for the test. You got to, quizzes, tests, you got to know this. What is it proportional to, class? It's proportional to rho s, and it's divided by 2 epsilon naught. Isn't that right? Now that would be the magnitude. What is the direction always, class? A normal. It's the normal direction to the plane, right? And if you're above it, it's positive z. If you're below it, it's minus z. Y'all follow? So this is really a normal. And if you're above it, it would be rho s over 2 epsilon naught. Az, if you were below the plane, it would be minus az. Do y'all follow? All right, question. Just listen to me and answer it appropriately. I have an and this is a typical Wentworth problem. It's also something I give occasionally. Now, suppose, now listen carefully. It's hard for me to draw this. I have an infinite plane of charge. Let's call this x, this y, and this z. But my infinite plane of charge is going to be in the xz plane at y equals 0. Can you imagine? It's this way. I'm not going to throw it at you. But I thought. I have a story about something I did. One time I was in technical school, right out of college. Right out of high school. Didn't go right. So I was really tired and I put my hand down. I was in the back. I worked at it. And I was out cold. And this teacher asked me, so what is it? Beginsky, what is it? I'm out, nobody's moving away from me. So he took an eraser and just threw it. Bumped me right in the head. It was all this chalk dust around me. It was kind of a false sleep. The guy was an ex-Vietnam guy. He did 2 tours of duty in combat. And insubordination, he could not handle. He just went, probably didn't punch me. Anyway. So here's the charge density rho S there. That was long ago. I know. I would be sued, thrown out of the university. Anyway, that's rho S in that plane. Y'all follow me, class? Now suppose I do this. I put a point charge, say on the y-axis at y equals 5. So at y equals 5, I put a point charge Q. I could keep adding charges, but this is good enough. Got me on this? Listen. Listen. And I asked you to find a point between the origin and this charge where the electric field was 0. You hear me? I didn't put values on for a reason. How would you fashion the problem? Anybody? How about in the back, you guys? Hold on. Anybody? Go ahead. You gotta speak up.
Like the charge of the sheet, and then if you don't have this.
Well, if we know the charge of the sheet, we know the electric field from the sheet, right? Which way is the electric field from the sheet is in that direction, correct? The value would be what? Whatever rho S is over 2 epsilon naught. In this case, it would be in the positive y direction, right? Y'all agree? That plus whatever the electric field is from that charge, the Q, has to be 0, correct, class? Y'all with me? Now, if I was greater than this, if I was at a y greater than 5, you all see both electric fields would be in that direction. Is that it? So in order to get a 0 field, the point has to be somewhere between the two. Do you agree? Everybody? Hear me now. So you got the magnitude of this. Now what I can do if I wanted that, I'm just going to erase this. We know what the magnitude of the field is from that point charge, right? Please listen. So we're going to set that equal to the value of the electric field from this. This is important. I'm going to be at a distance y. This is at a distance y equal 5. So when I write the equation, it would be whatever Q is over 4 pi epsilon naught, and this distance squared. That distance squared would be what? 5 minus y squared. Do y'all follow me? Y'all see that? You got to take a subtraction. You got to go from that. You got to go from the point of observation to the point of origin as the distance, and you got to square it. Y'all follow me? How many see you could solve that problem? Y'all with me? Okay, now, in a nutshell, I covered the essence of what you need to know for the quiz. So now, without further ado, would you please take everything off your desk and put it down? I'm going to